properties of logarithms are going to be particularly important in the study of physics. Now, physicists, as a general rule, don't always evaluate the exact expression of the logarithm, but we use them to simplify the mathematics a good bit of the time, and we capitalize on their properties. Real quick, let's review what a logarithm actually is. And a logarithm is the inverse process of the exponent equation. And so we look at these key components here, and the logarithm has a base value, usually as a subscript right here, the b. And what this does is you have the base b taken of a number x, and this gives you the power that you have to raise that base to in order to obtain the number x here. In other words, the logarithm solves the equation b raised to the power a is equal to x. Now, this is the very fundamental definition of the logarithm, and we don't execute this process as much as you might think, but we do need to be familiar with the properties. First thing we need to discuss is a bit of notation. And so when you see the log function, log, without a subscript, that is always taken by definition to be log base 10. So in other words, whatever result you get is going to be the power that you're raising the number 10 to. You can have different bases for logarithms, and they don't always have to be whole numbers, as we shall see. In this case here, you have log base 8 or log base 2, common in computer programming. And a very important logarithm that we see in the study of advanced physics is log based e. Now, e is a number that is approximately 717 approximately. And this has a very special name in the form of the natural logarithm, abbreviated as ln. And you'll actually see natural logarithms quite a bit, and it has to do with the relationships of numbers in advanced physics, and the number e turns up a lot in the equations of nature. But the purposes here are to discuss the properties of logarithms, and the properties apply to both the log function and the natural log function, as we see that it is equivalent to say log based e is the natural log. So let's look at this in the form of an example, and we will discuss each property in turn. Now, some of these are not quite intuitive, so you have to be a little bit careful and you have to think about them for a little bit to see how they go. So from chapter 0, we're going to take problem 26C, and we'll be able to illustrate the vast majority of the logarithm properties that we need to. Now, the first thing we need to do is we need to convert the radical sign into an appropriate power function. And you should remember from algebra that square roots or roots of any kind are fractional powers. In the case of the square root, that is the same thing as raising something to the 1/2 power that we see right here. And that leads us to our first rule. Since logarithms are actually the inverse of power functions or of exponentiation, the first thing that we're able to do, this is number 1, is that we see that logarithmic powers, so powers inside the logarithm function, can be brought down as coefficients. And so in this case, we see the 1/2 power is brought down to the front of the logarithm as a coefficient 1/2. And this, if you go back and examine what the logarithm function really is, and with a little bit of thought and a little bit of mathematical manipulation, you will be able to see why this is the case. And so we bring this down now, and we have the expression 1/2 times the logarithm of x squared times y to the 6th divided by z cubed. We will carry forward with that expression, and we will obtain either the second or third rule, depending on which order you do it in. Either order would be valid, but we're going to do this one first. And so the second property of logarithms that we want to examine is that logarithmic division, so division within the logarithm, is the same as the difference of individual logarithms. And so what we see is the general rule that the logarithm of a over b is equal to the logarithm of a minus the logarithm of b. And notice that b is just in there explicitly. It's not a fraction. And so we execute that process, and now we are left with the coefficient 1/2, and since this is now on the front here, it has to apply to everything inside the log function. So we keep it on the outside of the large brackets here, but inside we see the log of the numerator minus the log of the denominator. And so that is our second rule, that the logarithmic division is equivalent to the difference between the log of the numerator and the log of the denominator. Moving on from there, we'll take our expression from the bottom of the previous page, and we have it again up here at the top. And we execute our third rule, that logarithmic multiplication is the same as the addition of two logarithms. And so we see here that we have x squared times y to the 6th inside a logarithm function here. And this has been separated from the one over here, so we don't have to worry about it. We can simply treat this as an isolated function. Keep in mind the 1/2 has to stay on the outside and apply to everything. And so here, we can split this up into the log of x squared plus the log of y to the 6th. And so now we have an expression where we have 1/2 times the log of x squared plus the log of y to the 6th minus the log of z cubed, all inside the brackets here. So the 1/2 must apply to everything. Now, in order to solve the problem completely, it asks for the logarithm in terms of x, y, and z, all to the first power. So we have to do something about these powers here, here, and here. And now we have a complete set of rules that we can utilize in order to deal with those. Powers inside logarithms, again, can come down as coefficients. And so we end up log of x squared gives us 2 times the log of x. Log of y to the 6th gives us 6 times the log of y. And then log of z cubed gives us 3 times the log of z when the powers come down. And then from there, we distribute in our 1/2 now. You see now that we have 2 divided by 2 here, 6 divided by 2 here, and 3 divided by 2 here. So we've distributed the 1/2 in. And from there, we can simplify into the log of x plus 3 times the log of y minus 3/2 times the log of z. And so we have now achieved what the problem asks us to do, and we have developed 3 rules according to the properties of logarithms that you will find very useful in your study of physics from here on out. And we have indeed verified that the log of the square root of the quantity x squared y to the 6th divided by z cubed is equal to the log of x plus 3 times the log of y minus 3/2 times the log of z. And I encourage you to go back and review the rules of exponents and see if you can arrive at this same answer by a different method. Because remember, if we can arrive at the same answer by multiple different methods, we have confidence that our answer is correct.